Okay, it's recording. Thank you. Thank you. All right. So here is the carbon, which is alpha next to the cyano group. Remember, the pKa's of these hydrogens is about 25. So they definitely are acidic. And so the base, and a couple of things to answer some questions when you guys sit down with me one-on-one through Zoom on your test. The reason why some of you lost points is you didn't show your lone pairs, or you forgot to put in the charges. So every time you don't show a lone pair that you're going to use, that's a minus 0.5, right? So make sure you don't forget your lone pairs, because that's kind of it gets sloppy when you show it. Okay. So the lone pair attacks one of these alpha hydrogens. It doesn't really matter. This collapses. Actually, I should draw this out. These electrons go on the nitrogen like so, like that. Okay. And this is like an enol, right? But it's like an imine. It's imine like, but that's my nucleophile that I'm going to use to couple the reaction in a little bit. So I formed an enolate, even though it's not an enolate, this is more of a, I never know exactly what to call this thing, but it's like an imine. Yeah, like an imine, very similar to an imine. All right, so I take this and I react it next. This step is a one-way step, and I react it with the aldehyde. And of course, this is nucleophilic addition to the carbonyl carbons, you know, and it'll help you. I mean, this is carbon 1, carbon 2, carbon 3. The coupling will occur between carbons 2 and 3. So the lone pairs of the nitrogen, they drop down just like it did when it was like a carbonyl. Then the pi bond attacks the carbonyl carbons. Make sure it's attacking the carbonyl. Once again, some mistakes I saw in the exam, people were attacking bonds, you know, and not the atom in question. Or they would do things like this. You would do stuff like that. It's in space, it's not exactly on the atom. So make sure that you're very, very careful to show me what you're talking about. So it attacks the carbonyl carbon, and the electrons go up onto the carbonyl oxygen like so. As I always say, you have to be a gymnast of sorts. So I'm going to swing this hydrogen down. And now the coupling occurs between carbons 2 and 3. So yeah, coupling occurs here. And once again, notice this arrow is irreversible because I formed a carbon-carbon bond, which most of you did well on your mechanisms with that, but some of you still need to sure up when you use equilibria versus irreversible reaction. So Carbon-carbon bonds to the organic chemist generally means irreversible. Although in the real world, anything is possible, right? But for us, that's pretty much how you want to look at that. Next. Even though I'm under basic conditions, water is still available to me for the protonation of this step. Water is still available to me. So I have the beta I've formed the beta hydroxynitrile. Once again, the carbon adjacent to the nitrile is alpha. That carbon is beta, therefore it's a beta hydroxy. Now, there's a couple of ways I can look at this now. I can, and I'm going to actually shortcut here. If I take this nitrile at this point and treat it with 2 moles of hydrogen gas and any catalyst, whether it's lead or nickel or palladium, it will reduce. It reduces the nitrile to this amino group. In fact, I'm going to draw it out in green. Wait a minute, it'll be so visible. You get a reduction of the nitrile to the amino group, like so. That's what happens there. Or at this point, and this is maybe what the question was really leading to, there's always different ways to deal with stuff. Or, if I want to, I can go through the dehydration of this. Since I'm still in the basic condition, I can add heat, because I'm still in the base. I can go through a dehydration of this aldo-like product. And dehydration will work, because if I recategorize these carbon atoms, if carbon was hydroxyl is alpha now, that's my beta carbon, because I'm reclassifying what the carbons are called. That proton is most likely anti to the hydroxy. So this is definitely an E2 dehydration step. I'm going to lose water. So the hydroxyl, once again, I got my electrons. I have hydrogen, that collapses and kicks out. Oh, I thought it was a question. Okay. And I formed this alpha beta, the alpha beta unsaturated nitrile complex. But if I take that product and I treat it with excess hydrogen gas, I'll just say nickel. Just remind ourselves there's different catalysts that we can use. And I'm saying excess, I need at least 3 moles of this. I can add hydrogen across all those pipelines. giving us this bone problem, which is an extended amine.
Mr. Criss,
Yeah.
are the quizzes still bonus points on our grade? Like extra points?
Yeah. Mm-hmm. Yeah.
Thank you.
Yeah. Let me see. Someone's asking a question. So it is better. Okay, good. Good. Can you go over the basic nitro mechanism? Is that still a question? I'm not sure. Is the basic nitro mechanism still a question? Okay, all right.
Dexter, hold on. Before you
Yeah,
leave,
sorry.
can you take a picture?
Go ahead. What's that? I'm sorry, I didn't hear you.
Oh no, I was just gonna take a picture of the board before you leave.
Oh, okay, good idea. Okay. So I am recording to Zoom, but as some of you know, it takes about 36 hours before it's available to us. So.
Thank you.
So I can erase now?
Yeah.
Okay, all right. So there's a question on the board about the basic nitro mechanism. Well, I'm going to erase it now. I'm going to say something before I forget it. So this is just so I won't forget to talk about it. So this week there will be no virtual lab for you to, any new ones, right? Make sure I understand what I'm saying. Whatever you have to turn in, I think is due this week, right? From last week. But there's only one lab left, and we will present that lab next week for you to do. And that takes care of all of the virtual labs for the semester, okay? Trying to remember. And I will start, well, I graded like the first that deals Alder, that one's done. I got to grade the rest of them now and catch up in that regard. I will also post, because I finished up the Robertson annulation in the Michael edition for the virtual lecture. I just got to finish polishing it up, but that should be up tomorrow. If not tonight, but definitely by tomorrow, you'll have those to add to your collection. Far as the syllabus is concerned, we won't finish the whole thing now. That's one reason why I'm only doing 3 exams instead of 4. But I'm still going to drop the lowest exam score, okay? And I guess for some of you that works out really well because you have such good grades, some of you, the 3rd exam really can't hurt you because you can drop it. So I still encourage you, and I'm talking to those students who have like already an A with the first 2 exams, I still encourage you to work hard because a lot of what we're doing now reflects toward biochemistry. And you want to make sure that you have more understanding than the first 2 exams, which doesn't lean, the first 2 exams kind of finish up organic. What we're doing now steps into biochem. So make sure you're still keeping your nose to the, as the old folks say, the grinding stone, because you don't want to go to biochemistry and you didn't put the same amount of effort in, okay? All right, so the nitro. Trying to think of a good one. Of a good one to do for you. Okay, all right. So this is nitroaldol reaction. And there's been a request that I go through the mechanism for the basic reaction for this. Here I have an aldehyde, and as I said before, these are cross reactions because the two reagents are different. So here's an aldehyde. This one contains with no alpha hydrogen. And this is my nitro compound with an alpha hydrogen under basic conditions. So when I put this together, when I do a site reaction, I purposely make sure this one didn't contain any acidic hydrogens on purpose, just to make the flow go better. Now, if I know in all of these, I'm going to make the beta hydroxy. There's that CH2. I lose a hydrogen, and then have NO2. But what happens at this point spontaneously? What happens here? Anybody know? This carbon is alpha to the nitro group. That carbon is beta. So that I have my beta hydroxy nitro compound. But am I done? Is something else going to happen?
Sure.
What's going to happen? Anybody know? Based on what I talked about before. Dehydration? You guys agree with that? Well, yeah, you're right. That's dehydration. I'm going to wait just a second. I'm not seeing everybody. There we go. Okay. And the wrong view. Okay. Yeah, so dehydration. So the reason why dehydration occurs is because in relation to the nitro group, these hydrogens are extremely acidic. You know, I didn't even talk about that. I mean, here, these hydrogens has a pKa of approximately 10. Very, very acidic. So, whereas with the nitrile group and the aldehyde group that we looked at before, the pKa's were about 20 or 25, and the reaction would stop. But this is sorry, these hydrogens are so acidic that I'm going to lose water right across here. Very good, very good. I think that was Rachel. Very good. Now, this is actually a reversible step, but it happens. And if I were to show it mechanistically, or at least what's happening, it's because I'm under basic conditions. I don't even need heat for this to happen. It's going to dehydrate automatically. So dehydration occurs, and this is not the mechanism. This is just sighting through the reaction. We'll do the mechanism in a second. And now I have formed the alpha beta, unsaturated nitrogen. Like so. So let's go through the mechanism of this. Here when I need two. This is where I missed having my second board. You wouldn't be able to see it. So I'm going to erase this stuff from the bottom just so I can have some room. So I have my mechanism. Remember, this is important. I have two compounds, which I'll label A and B. the question I have for you to think about, which compound, A or B, will I use to form the enolate or the enolate-like intermediate? Which one will I use, A or B? Just like you said, B. Yeah, that's right. I'm going to use B. Why will I use B and not A? What does B contain that A doesn't contain?
Alpha hydrogens.
Yeah, the alpha hydrogens. And the alpha hydrogens, of course, are acidic. So that's what I'm going to start with. So I am under basic conditions. I'm going to see if I can get more light on the board down to this focus. Once again, the pKa of these hydrogens is approximately 10 because the nitro group is so electron withdrawing. It just drops the acidity of these, well, the pKa, making it more acidic, of those hydrogens. So the base is more than able, and I can grab any of these hydrogens. I'm just going to grab this one, just kind of shake it up and make sure you see what's happening. So the hydroxide can pull this alpha hydrogen away. That go, well, I need to draw this out, sorry, I'm going to do the mechanism. So this is nitrogen. Like so. The electrons go on to the oxygen. And I think in the video, I left out a plus charge someplace in one of those. I was looking back through it, like, you know. So make sure you keep up with the charges. I think I screwed up one of them. All right, so I have this is kind of like my enolate, all right, kind of like the imine with those oxygens attached to it. So now it reacts with this aldehyde. So this is chapter 16, nucleophilic addition to the carbonyl carbons. Now this is a coupling step. Once again, if I keep track of things. So I'll call this carbon 1, carbon 2, 3, 4, 5, 6. So coupling should occur between carbon 1 and carbons 2. That's where coupling should occur. So the electrons and oxygen drop down, the pi bond attacks the carbonyl carbon, that's coupling, that's nucleophilic addition to carbonyl carbon, that's chapter 16. And the pi bonds go up on the oxygen like so. So this is my coupling step. So I want to draw this into the left. Because as I talk about being a creature of habit, I try to always draw my enols or enolates or these emanates, I don't know what they're called, to the right. So I'm going to draw this into the left. Once again, I have to be a gymnast, so I'm gonna swing this hydrogen down. Oh, where'd it go? Okay, there it is. That's my nitrogen, double bond is back. Like so. Now water is available. Just pulls the proton off. And I'm going to condense this NO2 down to save little space. All right, so I have formed, this is alpha, this is beta. So we have formed the beta. We formed a beta hydroxy nitrogen. And then of course it's spontaneous. At this point, I'm just kind of taking some shortcuts because I don't have much space here. It's spontaneous that we're under basic conditions, once again, because if I reclassify, I'm going to erase this. If I were to reclassify my carbons and classify this carbon as alpha and that carbon as beta in relation to the OH group, then E2 elimination can occur, where electrons from the base will attack that beta hydrogen. This collapses and kicks up the hydroxide, and it gives us the final product. And all that happens without heat, the dehydration. Check in the questions here. Okay, so while some of you guys are writing, one of the questions is, am I going to write the quiz on the board? Yes, I'm going to write the quiz on the board before this session is done. What I want you to do, and then it's due, like I said, today by 3 o'clock. And I'll open up a Moodle page for you to turn that in. So I did the basic mechanism. The question is, will I email a copy of the quiz? I mean, I can, I'm gonna write it, and when you sit on the board, you realize I don't really have to, but I can do that when I'm done. Next question, on the exam, there was a question about choosing the most acidic hydrogen. Can you please go over that? Okay. Anybody need me to hold up before I erase this? So I can erase? Okay, erasing.
Dexter?
Yes.
It's kind of blurry again for some reason.
Oh, really?
Yeah.
What? I wonder what the heck is going on. Blurry like you can't read it blurry, huh?
Yeah, kind of like right before you erased it, but I don't know.
What's that?
Like right before you erased it, it was pretty hard to see. Like it was pretty blurry.
But it wasn't blurry, then it went blurry. Like that. So I don't
Yeah,
know.
yeah.
Okay. All right, so I'll try to make sure I rank large. All right, so there was a question on the exam. About acidity, and now remember there's 6 different versions. I'm just going to go over a couple to kind of give you some understanding. So remember, in general, we're talking about these. Can you see that? Is that blurry?
It's blurry, but I can see it. Like, cause it's big enough. But
Yeah.
but it's still pretty blurry.
Ah,
But we can probably I think most people can see that though.
You can still see it. You wrote big enough.
Yeah.
okay. All right. So remember, this carbon is alpha, right? We all know that. Which means that all of these hydrogens are acidic. And what do we mean by they're acidic? They're acidic because the pKa of each one of those hydrogens is approximately 20. Now, the reason why we say that's acidic, normally a hydrogen that's attached to a carbon, normally the pKa is approximately 50. So the pKa definitely dropped a lot for these hydrogens, because I have a hydrogen that's attached to a carbon, But I have 2 things going for me that's going to make this more acidic. And most of you know this. One, because of this carbonyl oxygen, electronic effects pull electron density, and I'm gonna focus on this hydrogen. I just want to focus on that bond. The reason, the way acidity works is we're talking about the electronic density between hydrogen and carbon. I'm just picking that out, okay? The more electronic density you have, the stronger this bond is. The stronger that bond, the less acidic it is, okay? So the stronger the bond, the more electronic density, the weaker the acid. But if the electronic density is low, then that means this bond is a weak bond, making this proton extremely acidic. So as you remove electronic density away, you make this hydrogen acidic. So that's what the carbonyl is doing. The carbonyl is sifting electronic density away from this hydrogen to itself, making this bond weak, therefore increasing the acidity and dropping the pKa to where it's more acidic now. That's the electronic effects, okay? Resonance is another reason. So I'm going to right over here. So I'm gonna just redraw it. Now, another reason why these hydrogens are so acidic is because of what happens after you pull the proton away. So if I go through the reaction and I use a base, some base, doesn't matter what it is, and the base comes in and removes, I'm going to remove this hydrogen, okay? The proton. Now, I don't normally show it this way, but I'm going to show it this way for teaching purposes. I'm going to leave those electrons in place, like so. So I had the base remove the hydrogen, but I left the electrons on the carbon. Make sure you can see that. So I'm going to leave the electrons on that carbon atom. You with me? Now, of course, this carbon bears a negative charge, and that carbon, if we were to classify it, is a carbanion. And carbanions are reactive. But resonance, a double-headed arrow, allows us to delocalize these electrons. So I can delocalize delocalization of those electrons will occur. Giving us this other contributor. So I basically have two contributors or resonance structures, 1 and 2. So why does that matter? Well, the more contributors or resonance structures you form, the more you stabilize molecules, species, whatever you want to call it. And so it helps to push this reaction more to the right. It helps to place it more to the right because I have additional contributors to shore it up. It makes it more stable by delocalization of the electrons as well as delocalization of the charge. And so anytime you can do that, that brings about stabilization. So the other one, of course, is resonance. So those are the two big reasons why it occurs. Now, on the test, well, let me back and explain something. If you had taken that same question in class with everyone, this would be the extent of what you had to do. But because you had a 3-hour window, basically, to take the test, I had to make you, I had to present you a more rigorous problem to consider, okay? Based on information we talked about in class, and that's basically lecture, but then I could give you something that was a little bit more challenging. And so some of you got different kind of looking questions. But if you understand this basic idea, the idea from my perspective is, and I don't know if this is the problem or not, because like I said, there's 6 different ones. So let's label these A, B, C, D, E, F. Can everyone see those? Do I need to draw it bigger or something? Just want to make sure I have everybody's.
That's good.
Mm-hmm.
Okay. All right. So based on, okay. So based on what we just discussed, which hydrogen would be most acidic? And the way you guys are thinking, I go to the chat line because sometimes people answer it in the chat.
Would it be hydrogen C?
C? C's on the table. Seems like a good choice. Anybody else?
Dexter, can you readjust the camera again? It got blurry.
Yeah, I don't know what's going on.
It's every time you move it, that's when that happens.
Move the camera? Oh, let's see. Should I kick it? I don't know. Is it still blurry?
No.
Well, let me do this. I'll just bring it closer. Does that help with what we're doing?
It's a little better.
Wow, I have no idea why in the heck it's blurry. This is the same camera I've been using since we went into all this. But you can see it though, right?
Yeah.
Okay. All right, so C, anybody want to dispute or go along with that? Go along with it? So, okay, there's a good question out there. Why not B? So for the sake of speaking, I agree. Either C or B would be the two in question for the two reasons we talked about. Electronic effects, they're both in the alpha position to the carbonyl, and what? Resonance can occur with both of them, right? But with that, which one would be most acidic? And that's the rigorous part I was talking about. Well, let's think about it. If you look at C, from resonance is going to be the same for both B and C. They're both going to form two contributors. The only thing that's going to be different about the two is the electronic effects. So if you look at C, there is a hydrogen there. Whereas with B, there's a methyl group. Electronically, which one is more electron donating? Will it be the hydrogen or will it be the methyl group? Which one is more electron donating, the hydrogen or the methyl group?
Oh, hydrogen.
What?
Methyl group.
You okay? So which one did you say? Which one is more electron donating, the hydrogen or the methyl? I hear no response. Anyone? Y'all leave me hanging?
The methyl?
The methyl, yeah. So the methyl group is more electron donating. So if it's more electron donating, what is it doing to this bond? Which I am going to draw this out so you can see it. Just gonna make this bond dark, but we're talking about this bond here as well as here. This is C and this is B, right? So resonance-wise, it's the same. Both are going to form two contributors. The only thing that's different is the electronic density of HB and HC. The methyl group, if it's an electron donating group, then will it increase electronic density or will it decrease electronic density? Will it increase electronic density here or make it less? Someone answered through here. Let's see what they said. Increase. Okay, very good. I keep pressing the wrong button. There we go. That's right. It's going to increase the electronic density. And if it increases the electronic density, will it increase or decrease the acidity of HB? Will it become more acidic or less acidic?
Less.
More acidic. I'm sorry, what's that?
Less.
Less, there you go. It becomes less acidic compared to HC. And the reason I said that hydrogen is neutral. I can spell neutral. The hydrogen here is neutral. It doesn't really add anything to the electronic density. So because of that, this is what it is, but the methyl group actually makes this bond more electron rich, which makes C the stronger acid. That was one example. Now I'm gonna swing over here.
Dexter,
Yeah.
can I have another Zoom to go to? So can we do the quiz soon?
Yeah, good idea. We only got 5 minutes left, right?
Yeah.
Okay. This thing is on the, I got it rigged up where it may fall anything. Sorry. Okay, your quiz